Hello and welcome to my video about the ball drop. I'm going to cut the video here and you're going to go over to over there where I'm going to actually do the ball drop. I want you to try to see if you can collect the data yourself and then compare your results to mine, and then see if you can make the same graphs that I get. I have two different balls here that are approximately the same size, so they have about the same surface area, but they're different weights, okay? They have different masses. So we're gonna drop one at a time, and we're gonna, you can slow down the footage to try to see if you can calculate gravity. I'll put a link to the Google Sheet in the video, and I'll also explain how to do the Google Sheets in later on in this video. But first of all, we've got the tennis ball in green, and we've got like a just a regular like ball pit blue ball. So it's basically hollow and fairly light. We're going to drop one at a time, maybe starting with the blue ball. And the question is, are they going to hit the ground at the same time? So the classic explanation that you're given is that all things in gravity fall at the same rate. So let's just drop the blue ball and see what happens. We're going to do the green ball and see what happens. Okay, and then here I'm going to try to drop both at the same time. We'll see how this ends up working with one hand, but we'll see if we can see a difference. All right, so you may have seen at the end there that the green ball hit first. So why is that? And let's do some calculations on it. All right, so a continuation of this ball drop. This is what I ended up with. Now, this is for the blue ball. And what I did here is each of those little sticky notes corresponds to 1 meter on the measuring tape. So what I did is I just used that and then got my time based off of that from the slow motion video. Now, when you do that, you're going to notice that your data is going to bounce around a little bit. You're going to have some funny stuff going on like this right here, which really changes the meaning of your data. This happens because between those different times, it basically, the position changed really, really quickly. So we don't have enough detail to be able to tell what the velocity is there. Also, what you're going to notice is that there's a big gap for the first couple data points, and then it speeds up considerably down at the bottom. So you can see on the position time graph, there's a big gap of data right here. We don't have anything, and there's a lot of data clumped up down here at the bottom, which will affect things quite a bit. So here we have a couple zeros, for example, no acceleration. That's weird. In the acceleration data, we have all the way from negative 18.5 to positive 18.5. And our data bounces around quite a bit. So you can see that here on the acceleration graph. We've got positive 18 and negative 18 and a half. So that's pretty significant. Then what I did is, instead of making my distance the manipulated variable, I made my time my manipulated variable. And that's really what we're doing realistically, is we're manipulating time. So that's why time's on the x-axis, et cetera, et cetera. So what we're going to do is try that again. Here's the new data, where I tried to basically take a data point every 0.1 seconds. Sometimes the stopwatch doesn't let you do that because the stopwatch is not super consistent, but I tried to take one every 0.1 seconds. So that's my results there. These are just my best estimates based off of where the ball was in relationship to the two sticky notes above and below. And then I did the same thing with the tennis ball. So if you don't want to go through the slow motion video and get your own data, try this data for the blue ball. Pause the video, try it out, and try this data for the tennis ball. Pause the video and try it out. Okay, so now I'm going to go through and explain really how Google Docs work. Google Docs are pretty special because they allow us to do calculations without having to type it in our calculator. And they allow us to do many calculations all at once. So, for example, here our adjusted time is when we're going to say the original time is what we're going to subtract from. So we're going to subtract by, and that went really quickly, but it'll even like suggest to pull it down for you, which is nice. But basically every single one of these, if you press enter, it'll highlight in orange the cell that it's using, A39, and then you subtract by the original time. And you can see that all of them, if you look at the top here, all of them have the same formula, right? It's just A40 whatever minus the 363. So by doing that, we have adjusted it so that our start time is 0 and it goes on from there. So that's what's going on. So now that we've done that, we can now also adjust. This is in feet, which is a problem. So what we're going to do is we're going to adjust that by taking the feet number and we're going to multiply it by 0.3048 is the conversion ratio. So once you've done it one time, it will automatically populate down. Now, if it doesn't automatically populate down, how can you do that? If you click on the cell with the formula, you can click and drag it down. Where am I clicking? I'm clicking right on this blue circle here. Click and drag it down. Now, if you click and drag it down, mostly that'll work. Down here, you'll notice it's 0 times whatever. Here, you'll notice that a blank cell counts as a 0. So it is automatically doing those calculations, but we don't want it to. So we're going to stop there. Now, we are using instantaneous velocity. Actually, let's graph this guy and see what that looks like first. So first of all, we're going to click, we're going to select the cells that we want, including the titles. Now in the titles, I have my units. In below, I just have numbers. I'm going to click insert chart, and automatically it should really insert the correct chart. But if it doesn't, there are a few things you can do to make sure that it is the nicest chart. So first of all, in the setup, you can click scatter chart. That's what you want, scatter plot, scatter chart. In the x-axis, you want to have your time. In the series position, you want to have your manipulated or your responding variable, which is your position. Then if we click customize, we can go down to series and we can add a trend line, which is lovely. Now, is this linear? Nope. It is polynomial, degree 2, and use equation. Now, in this context, the equation here does not help us because it's physics 20, but it will help us in the next graph. So let's do that. Let's look at the next graph. When we find instantaneous velocity, let's just look at the velocity part first. I think more people are okay with this. We take the first position, the first y, so y2 minus y1 divided by x2 minus x1 in brackets. So it's y2 minus y1 over x2 minus x1. Now, if you press enter, it has now done that calculation once, right? Now, if we drag that down, let's just drag it down here. It will give it divided by 0 because these are all zeros here. So it'll know that that's an error, but this one's also an error. And it's because, look at that. If we select it, it's taking these two cells, right? So we don't want that one to exist. We're going to delete that one. Now, the time is an average between the two positions. Now, we should hopefully know how to do an average. We take this one plus this one divided by 2 because there's two objects. So we can do that and we can get an average. This is fantastic and wonderful, but now we can graph the thing. So we're going to go Insert, Chart. Alrighty, there it is. So we've got our scatter chart. Now we can click Customize, Series, down here for Legend, Linear. Yes, this one should be linear, and use equation. Now the equation here you can see is y equals mx plus b, right? So this m part is the slope of this line, right? The value beside the x is the slope of the line. So that is our acceleration felt throughout the situation. Now, it doesn't look super linear. It actually looks like it's kind of curving down like this. Like it's sharper at the beginning, and then it gets flatter at the end. And that's true, and we'll talk about that. But let's take a look at the next one. So here, we can do the exact same thing again. Actually, let's do this. The exact same thing again. We're going to go y2 minus y1 divided by x2 minus x1 in brackets. The other thing we're going to do is, for time, we're going to make it an average. So we already knew how to do average, but now we're going to do it a different way. We're going to take an average of those two. The nice thing is, a lot of these functions can be done in Google Sheets or Excel. And we also, just if you didn't notice that there, but we were able to drag down that formula from both boxes, not just one box. You can, if you have a whole set of boxes, you can just drag the whole thing down and it'll go with you. So it's pretty wonderful. Okay, so now we can do one more graph. We're going to have the acceleration time graph. It's going to look like this. I'm just moving it into position here. Just a reminder to add your trend line, and this one should be linear. Oh, I guess I could have had the equation on here as well. This one should be linear, and it will be linear, but it should be flat. And this doesn't really show that well. It's because it bounces around a lot. That's the error in the measurement, but that's okay. You'll notice that we have better measurement now than we did for the previous data. This is going from -17 to like +2 ish, right? So it's going between those two, whereas this was +18 to -18. So it's worse in the previous one. So again, the difference between this and the last one is simply that we changed and made our time manipulated. That's what you should really do every 0.1 seconds. Okay, now let's look at the tennis ball and basically do the exact same thing to it. So literally the exact same thing to it. I could click and drag down these same formulas down here and it would actually work. I won't do that. I'm going to click it in again, but pause the video here, see if you can do this, and then press play. All right, there's our adjusted time, and now our position. In meters instead of in feet, so the unit conversion there. Here we're going to have time as an average of the previous two, because we're doing, whoops, spelled that wrong. There you go. And we're going to get the instant velocity. So we're going to go y2 minus y1 bracket divided by x2 minus x1. Said that wrong twice now. Okay, and then this one will be average of these two, which there's nothing there right now, but we're going to see it pop up in a second. This is going to be bracket this one minus this one bracket divided by this one minus this one bracket. And we can now drag this whole thing down. Boom. And there's our data. So let's go ahead and now try this out. We're going to take this and insert chart. Here's our data. We're going to add our polynomial trend line. The equation is not important for this one because it doesn't mean anything to us in Physics 20. Here's the velocity time graph. This one should be linear, and the equation is important in this case. I made a mistake, but I will show it in a second. And I can fix it in a second. That's the nice thing. So anyways, let's go ahead and put this over here. We're going to do the same thing. Okay, so I don't know if anyone can recognize my mistake right now, but it's something that I warned about in the last one. The issue is right here. If you take a look at this formula, it is using these blank cells in order to calculate, which is going to cause an error, well, a 0 to show up. And then you're going to have an error here, but if you look up, same sort of thing is happening. You can see it's using G83 and F83, so those ones also need to be deleted. And if you look at that, we've got a acceleration now. Our m value, which is the slope of the velocity time graph, our acceleration is 9.73, which is pretty darn close to 9.81, slightly less than 9.81, which is interesting and important because if we're dropping a ball, we expect a little bit of air resistance, which would decrease the acceleration to be slightly less than gravity. So that makes sense. Also, if you compare it to our blue ball, which was very, very lightweight, this blue ball had an acceleration of about 6.5, whereas now we have 9.7. So it's much faster, higher acceleration, I should say. And that's because the tennis ball has more mass. If it has more mass, it's affected by force less. So the air resistance is affecting it less because the force is the same. Force of air resistance is roughly the same because they're both about the same size, surface area wise. So the only thing that's changing is the mass. So F equals ma. If the F is the same and the mass goes up, that means the acceleration must go down. So it's being affected by air resistance less. So I hope that this video helps you better understand mostly how to do Google Sheets and pull these equations across, pull them down, and how to just generally speaking calculate within cells. There are a few different functions, but if you Google things, you can probably figure out the rest. But the main idea is this equal sign, brackets, subtracting, adding, the division. You can use a star for multiplying, or you could just have brackets next to other brackets, like you would in algebra. So I hope this video helps you better understand this stuff, and good luck.